Hello and welcome to the session today on an overview of the PLAXIS 2D LE software. My name is Murray Fredland and I'm happy to be giving this overview to you today. So today we are going to cover a little bit of an introduction to the software. We'll go through an overview of the main features of the software, some of the differentiating features, and lastly cover some examples that the software can be applied to and summarize the key benefits of the software. So Bentley Geotech Engineering has a comprehensive geotechnical suite of software that includes both geotechnical information systems and geotechnical analysis. On the geotechnical information side, we have the GINT, Open Ground, and Kinetic software to use to manage borehole information in the field. And on the geotech analysis side, we have PLAXIS LE, which was previously known as SV Slope, and PLAXIS 2D 3D finite element software, and PLAXIS Designer, which is 3D conceptual modeling software. So to give you just a little bit of an idea of the overview of PLAXIS LE, it is software for performing deterministic and probabilistic analysis of soil and rock slopes in 2D and 3D. You can calculate the factor of safety, the probability of unsatisfactory performance, or the reliability index of the software. The software is designed to be easy to use and yet offer advanced features that can facilitate the analysis of real-world complex geometries and geotechnical conditions, including groundwater seepage. It also contains comprehensive support for reinforced slopes and external loadings in the software. The package consists of a blend of classic method of slices analysis, new probabilistic analysis methods, and advanced searching algorithms. And the software has been put together by a world-class team of developers, and there's very advanced new methods of analysis integrated with classic methods in a very comprehensive and easy-to-use user interface. In terms of workflow, it's important to realize when you're building a problem that you are going from left to right through the menu system, and fundamentally that means that you're describing elements of a boundary value problem, and that there is three fundamental aspects of the model that you have to describe. That is geometry, materials, and boundary conditions. And all three of those are menu options on the top menu. The boundary conditions in slope stability really are comprised of loading conditions, so line loads, distributed seismic loads, and the supports are really, you have to define what type of support it is and where it is located in the model. In terms of geometry, the software offers a very nice CAD-based type of control interface or window where you can draw the geometry of the problem similar to some type of CAD-based program. You can also use grids or snapping tools to make sure that your intersections line up exactly in the model. There's also extensive features for importing different file formats that contain geometry already, such as DXF file formats and other formats in the import menu. There's also geometry cleanup tools that can be accessed, such as point reduction, where you have too many points in the geometry and you want to reduce it so that you have a manageable number of points in a numerical model. You can do so in the cleanup menu. In terms of material properties, there is a comprehensive list of almost 30 material properties in the software, which can be categorized as drained, constitutive models, undrained, rock mechanics, or unsaturated soil types of constitutive models. And those can be accessed in the groundwater modeling part of it. We have the Soil Vision Soils database of over 40,000 soils that can be accessed, and you can pull up example materials which contain a soil water characteristic curve of the type of material you want to model, or you can use some of the estimation methods that allow you to predict soil water characteristic curves based on simpler properties such as grain size distributions. So as well as part of the package, when we did development early on, we found that the biggest source of variability in the software is whether or not you have found the critical slip surface. Therefore, we shifted the development to implement more searching algorithms, and as such, there are a comprehensive list of searching algorithms in the software that can allow you to search both circular and non-circular slip surfaces and confirm that you're finding the most critical slip surface. Searches such as Greco search, Cuckoo search methods can be implemented, and then optimization techniques take a circular or a non-circular slip surface and break it into line segments and further optimize the solution to try to make sure that you have the critical slip surface. There are multiple ways to analyze pore water pressures and include those in your analysis, such as water tables, piezometric surfaces, R sub U values, discrete points. You can pull pore water pressures in from the groundwater package or model unsaturated suctions, and this is all for modeling in an effective stress analysis. Loadings can be entered into the software quite easily by graphically placing a load on a certain line segment that's a boundary segment. You can enter distributed loads, point loads, or seismic loads into the software. There's also several methods of handling seismic analysis in the software. Firstly, there is the most basic pseudo-static method that's been implemented. It's a very direct and simple method is one of the advantages. It's similar to a static analysis using a limit equilibrium. It's easy to implement in the software, but it has some disadvantages due to the simplicity of the method. So some of the disadvantages of the pseudo-static method are that it replaces a shaking motion with a single permanent force acting in one direction. It also ignores the dynamic response of any structure and the frequency content of the seismic movement. It's subjective to the choice of the pseudo-static coefficient, which there is somewhat diverse opinions in the industry on how to apply it. It typically results in forcing the slip surface very deep, which may be a little bit unnatural in terms of where the actual slip surface is. And there's no consensus as well as on one of the final factors safety should be by this method. So researchers have improved on this method and proposed the Spectral seismic analysis method, which is implemented in the software as well, and it has been benchmarked against more rigorous finite element, finite difference methods. And in this case, the primary change here is that you're allowing your force that you're applying horizontally to vary with depth, so that a larger portion of the force is applied close to the ground surface, which is more realistic, and it tapers off as you go deeper into the slope. So with this method, the slip surface doesn't go deep, and it's been found to be more realistic in terms of the predicted factor of safety and the location of the critical slip surface. There is also a finite element seismic analysis implemented with the software, and in this case you can flip to a fully finite element module that you can put on boundary conditions and apply seismic loads and solve a finite element analysis of a 2D finite element analysis and incorporate those results into your limit equilibrium analysis. The software offers as well detailed support analysis and such methods, such anchors as grouted tiebacks, end anchors, soil nails, micropiles, and geotextiles can be included in the analysis quite easily. All these elements can be graphically drawn on the screen, and the properties of the members can be entered into the software. So to just look at some of the differentiating features, in other words, what makes the software different than other software packages currently available on the market, let's look at some of these features. Well, there is very much simplified model creation with PLAXIS Designer is one major feature. In other words, the ability to create 3D models is greatly simplified. There is a multiplane 2D analysis, which we'll get into that, which allows you to analyze many different 2D slices across a spatially varying 3D problem. The software has very advanced ability to model unsaturated and climatic seepage analysis. There is the implementation of rapid drawdown analysis either by the Duncan 3-stage total stress analysis or a combined effective stress analysis. There's advanced probabilistic analysis features. You can model spatial variability. There's also dynamic programming for searching for your critical slip surface, and very advanced block searching, bedding planes, and anisotropic rock mechanics for modeling rock slope stability in the software. There's also integration with the comprehensive PLAXIS finite element software package. So at the start, let's look at what is PLAXIS Designer. Well, PLAXIS Designer is a 3D geotech conceptual modeling software. It enables very complex three-dimensional compilation and visualization of all your 3D geotech site information in order to improve design. So it really pulls different data sources together and different information sources such as field instrumentation together in a three-dimensional comprehensive view such that you can examine and see where your data sources are, get a comprehensive view of the 3D geometry, and handle any pinch outs or any types of overlaps in the geometry definition. It allows really fast 2D spatial analysis modeling. So the PLAXIS Designer is good even if you're doing a two-dimensional analysis, and that you can build your site in 3D and then you can slice it at many different places to do a full two-dimensional limit equilibrium analysis. You can integrate boreholes into your 3D design. It's got advanced tools for intersecting surfaces, and you can pull in Internet of Things field data to further complement your analysis, such as piezometric data. So what does multiplane analysis or MPA analysis do? It allows the user to specify and analyze many 2D cross-sections of a 3D model. And so here we have an example of an earth dam where typically what you would do is you would take 2 or 3 cross-sections down the in the structure and analyze them in 2D for stability factor safety. The problem with this, however, is that you don't know where the critical location of the factor safety is, and you're just guessing in terms of where you would do your analysis and the orientation that you would do your analysis at. So what this allows you to do, MPA, is now on this earth dam, we can sweep a 2D analysis up and down both the upstream and downstream sides of the structure quite easily and get a fast response and a very spatially representative response of where our critical sections are for 2D analysis. So it allows tie-in to existing 2D methods and allows you to spread those into 3D quite nicely. So you're just basically doing a standard 2D limit equilibrium analysis, only you're spreading it hundreds or hundreds or thousands of times across a spatial 3D structure. So it's a very interesting way to partially scale up to 3D. Another thing that sets the software apart is its unsaturated climatic analysis. It has advanced features for modeling boundary conditions where there's rainfall and evaporation, and it calculates, more crucially, the actual evaporation from the soil surface, because we really can get an idea of potential evaporation, but the actual evaporation that is evaporated may be quite different than potential. And the software includes a rigorous Penman-Wilson boundary condition to model this. And so in cases where the mass balance depends very highly on actual evaporation from soil surfaces, this feature is extremely useful. In terms of rapid drawdown analysis, there are both total stress analysis methods implemented and effective stress analysis methods, such as for total stress, the Duncan 3-stage procedure, and effective stress analysis, coupling the groundwater and your limit equilibrium analysis can be accomplished. In terms of another competitive edge, the statistical analysis that can be performed with the software is very comprehensive. You can implement in your analysis the Monte Carlo, Latin hypercube, and alternate point estimate methods for analysis. And each of these methods have their advantages. Monte Carlo is very common in terms of sampling, but it has the downside is that you need a lot of trial runs to get a comprehensive statistical idea of your parameter variation. So you can't vary more than 3 or 4 parameters before the number of model runs becomes excessive. In the alternate point estimate method, you can keep the model runs quite low and still analyze the variability of a lot of different input parameters and generate tornado diagrams, which are shown here. And these tornado diagrams show which parameter has the ability to alter the factor of safety calculation by what amount. And so it's a very helpful type of analysis that shows really the relative influence of each of your input parameters on the ultimate factor of safety. Random fields have also been implemented in the software, and this model shows that, for example, where instead of just a homogeneous property on the layer above the bottom layer, what we've implemented is spatial variability of the friction angle of the soil, and therefore we can use that in the calculation of the factor safety. And the method works in deterministic analysis, and as well as if you want to do a probabilistic Monte Carlo analysis, you can set the spatial variation to generate a new spatial variability field on every single iteration of your Monte Carlo analysis. So it allows a very comprehensive type of analysis. There's also the advantage of the dynamic programming searching method, which is an unrestrained searching method to find the critical slip surface by hunting through a field of stresses calculated by a finite element analysis. So with this method, you have the more accurate and more the idealized way of using stress from a finite element analysis to calculate your stresses in the field. And this method is based on the traveling salesman algorithm that hunts through this to find the stress field, to find your minimum factor of safety or your minimum critical slip surface for your factor of safety. And it is a good method. You also have advanced block searching features that have been implemented in the software for based on points, lines, or blocks, which can be searched, and entry and exit angles. So you have a number of different methods that can be utilized for hunting and searching pieces of your slip surface and grouping that together in either a pseudo type of circular or a completely non-circular type of slip surface, such as those often found in rock mechanics. Other rock mechanics features include the implementation on the solution of weak surfaces, anisotropy, bedding guides, which can tell you what your anisotropy is at any point in space, and weak surfaces can be interpolated between bedding guides. So there's a very comprehensive method of analyzing rock mechanics and using bedding guides to handle anisotropy all in 3D. And these functions can be integrated with the typical rock mechanics constitutive models such as Hook-Brown generalized, Hook-Brown Barton-Bandus, and the ALM anisotropic linear models 1 to 4, which are typical in the analysis of rock slopes, particularly in open pit stability analysis. We also have PLAXIS integration, which 2D geometry transfer is now available to move geometry between PLAXIS and PLAXIS LE and analyze, for example, the same slope using both limit equilibrium and finite element shear strength reduction type of methodologies. So just some typical examples of how this might be used in practice are as follows. This shows a typical earth dam, and this can be analyzed via a total stress analysis. We're looking at a rapid drawdown scenario where your water table drops from the upper level to the lower level, and we're looking at analyzing rapid drawdown. So we can model this using a total stress, Duncan three-stage parameter, or three-stage type of analysis, or we can use a combined seepage and slope stability effective stress type of analysis where we consider the effect of pore water pressures and the influence of time on the speed at which you rapidly draw down the water table behind your earth structure. Embankments and roadways are a good example of an application of the software. This shows anchors and micropiles put into a slope, and as well as a load on the upper surface, and then the resulting critical slip surface calculated through these different patterns. And you can adjust your design to find out where your critical slip surface might end up. Embankment stability is another key application of the software, and here you can see a multi-soil different application where there is one layer is represented with spatial variability, and you can see the weak and strong zones represented in the soil slope. And another easy example of the software where we're using a non-linear or non-circular rather optimized slip surface as your critical slip surface. So in summary, the benefits of the software include a new 3D geometry manipulation and conceptualization module called PLAXIS Designer. There's the access to statistical methods and spatial variability that could provide a more comprehensive picture of the analysis. There's better searching methods to improve the chance of finding a true critical slip surface. And it's integrated with market-leading seepage analysis software, which can include unsaturated climatic analysis. There's also advanced rock anisotropy, and lastly, PLAXIS FEM integration. So thank you for your time in looking through this brief overview of PLAXIS 2D LE, and we would be happy to help you and assist you further in your application. Thank you.